I welcome all of you to the video lecture series on fluid mechanics. This lecture is on topic 5 on finite control volume based momentum analysis of flow systems. This lecture 15 is specifically on finite control volume based linear momentum analysis. There are two lectures corresponding to this topic. We are starting first with linear momentum analysis, and then we'll go to the angular momentum analysis. In fluid mechanics, there are basically two types of analysis: finite control volume based analysis and infinitesimal control volume based analysis. Finite control volume based analysis leads us to an integral equation, whereas infinitesimal control volume based analysis lead us to a differential equation in fluid mechanics. Now, the learning outcome or the learning objective of this topic on momentum analysis of flow system are as follows. If you go through this lecture, you are expected to learn that for a control volume, you should be able to identify various types of forces and moments. So for a fluid flow system, you should be able to identify a finite size of control volume, and you can demarcate the control volume and identify the forces and moments corresponding to that flow system. And furthermore, you should be able to do a control volume analysis, finite control volume based analysis, to determine the forces associated with the fluid flow system, as well as if the problem involves angular momentum, then you should be able to determine the moment caused by the fluid flow and the torque transmitted. This topic is based on Newton's second law, which basically is given as force is equals to mass into acceleration. However, in fluid mechanics, we convert the acceleration into the time-wise gradient of velocity and convert it into mass into acceleration into rate of change of momentum. And there are two types of momentum that we encounter. Here, what is presented is a linear momentum. Linear momentum is the product of mass and velocity, and the direction of linear momentum is in the direction of the velocity. So let us suppose this is a ball which is moving from left to right with a velocity of u. Then its momentum will be basically the mass of this ball multiplied by the velocity. So the direction of momentum is in the direction of the velocity. So as I said that the Newton's second law is equals to mass into acceleration. So what we do is we basically convert the acceleration into time-wise gradient of velocity, and we take this mass inside the differential. Then we end up with time-wise rate of change of linear momentum. So we correlate in fluid mechanics. Instead of defining force equals to mass into acceleration, we express the mass into acceleration as the rate of change of momentum, and we use force is equals to rate of change of linear momentum. However, if we have a system which involves moments, then we have moment is equals to, instead of mass, we have moment of inertia, and instead of linear acceleration, we have an angular acceleration. And that angular acceleration is given as time-wise rate of, here it's a linear velocity, here you have an angular velocity. And you finally end up with rate of change of angular momentum as shown here. So for rotating system, moment or torque is equals to moment of inertia into angular acceleration, which is expressed as time-wise rate of change of angular velocity. And finally, we end up with the rate of change of angular momentum. So Newton's law is expressed as rate of change of linear momentum or angular momentum is equals to force and moments respectively. This is as shown here. So this is rate of change of linear momentum. This is rate of change of angular momentum. Originally, this Newton's second law was proposed as time-wise rate of change of momentum of a body of matter, which in fluid mechanics could be a gas or a liquid, is equal to the net external force or moment applied on the body. So if you talk of rate of change of linear momentum, then this will be equal to net external force. If you talk of rate of change of angular momentum, then this will be equal to the moment applied on the body. Now note that this expression is given for in a non-accelerating frame of reference, which we call as inertial frame of reference, where the system that we are studying is either stationary or moving with constant velocity. The acceleration of the system is 0. So we said that the rate of change of momentum is equals to external force. So let us discuss what are the type of forces that are encountered in fluid mechanics. Mainly there are two types of forces which are presented here as surface force and body force. Surface force is due to interaction between the body and the matter in immediate contact with it and acts at the bounding surface. So I will show you later on that whenever we take up flow systems, there are certain forces like pressure and the viscous forces which acts on the surface of the fluid body or control volume, and it is surrounded by fluids which, like if you take a fluid body or a fluid control volume in a fluid flow region, then that fluid body is surrounded by the fluid which is having a different velocity, and the nearby velocity gradients leads to viscous forces because this fluid has certain viscosity, and from the adjoining fluid there is also a pressure force which acts on that fluid body. So the pressure force and the viscous force are the surface forces. Other than this, if you take a fluid body, there is another force which is a body force which acts on the bulk of the body due to gravity or magnetism. The fluid body, other than the surface force such as pressure and viscous forces, it will also encounter gravitational force. We express the intensity of surface force as force per unit area, which we call as stress, because this surface force is directly proportional to surface area. Whereas this body force, we express it as force per unit volume, since the body force is directly proportional to mass or volume. So this surface force are what you can call it as a flux variable, and this body force is a volumetric variable. If you consider a stationary fluid, then note that the force that acts corresponds to the pressure, which is a normal stress. So in a stationary fluid, you only have a normal stress. But if you consider fluid in motion, it has both normal and tangential stress. Pressure acts as a normal stress, and the viscous stress can be either normal or tangential. I'll show through a separate diagram. The body force that will be of interest in this lecture series will be due to gravity. So we are limiting our body force for this lecture series to gravity, not magnetism. So I mentioned that the surface force can be normal and tangential, both normal and tangential. So let me show you a fluid body or fluid control volume. And in this, I am showing you the stresses denoted by sigma. So the stress that I am showing you here, let me call this as viscous stress. Other than, so this is a surface force. So basically, each fluid has a thermophysical property which I introduced earlier called as dynamic viscosity, which is due to the stickiness between the different, each fluid has certain stickiness which leads to the resistance between the motion of the different layers of the fluid. So considering the velocity, there is certain, when you consider the velocity gradients and the viscosity, there are some viscous forces which act on a fluid control volume. So this, let's call this sigma as viscous stresses. Other than this, you will have pressure also as a stress, surface force term as a stress. So let me show you if these are the viscous stresses, the pressure I will show you separately. So the pressure always acts normal to the surface. So it will act in this direction. On this surface it will act. Pressure is always normal and compressive. So these are the direction of the pressure forces. So I'm saying sigma is your viscous stress, and these viscous stresses are expressed as, for a 2D case, there are only four stresses: sigma xx, sigma yy, sigma yx, and sigma xy. So sigma xx in fluid kinematics, we have obtained the relationship between the strain rate and the velocity gradient. In later topics, we'll correlate the stress with strain rate in fluid mechanics. And later on, I will show you the derivation where the sigma xx is given as 2 mu del u by del x, where u is the velocity in the x direction, and sigma yy is given as 2 mu del v by del y, and sigma yx is equals to sigma xy is equals to mu del u by del y plus del v by del x. Okay. So for a 2D case, I am here showing you that these viscous stresses are directly proportional to the viscosity, and they are function of velocity gradients, where the velocity u is the velocity in the horizontal or x direction, v is the velocity in the vertical direction, y direction. And the pressure is shown here as normal compressive stress. So we encounter two types of surface forces, as I had mentioned here, pressure and viscous forces. Note that this surface forces, when you express it in terms of stress, the stress is denoted by two directions. The first subscript, like if you see the first subscript of all the stress in this plane, sigma xx, sigma xy, sigma xz. The first script of all the stress is x. So the first subscript represents the plane in which the stress is acting. The direction of the plane is given by the normal. If you draw a normal from this vertical plane, the direction is x. The first subscript is representing the direction of the stress. The second subscript is representing the direction of, the first subscript is the direction of the plane. The second subscript is the direction of the stress. So the stress is represented by the direction of the plane and the direction in which it is acting. So the direction of the plane and the direction of the stress are same, sigma x, such as the sigma xx or sigma yy, they are normal stresses. And if they are not same, then it is a shear stress. Newton's second law cannot be applied directly in fluid mechanics due to the fact that it was proposed originally for a fixed body of matter, whereas in fluid mechanics, we prefer fixed region or control values preferred in fluid mechanics, where the matter contained within the control volume changes with time. So if you follow a fixed mass or body of matter, then in that case, for that case, originally the Newton's second law was proposed. Now we want to apply in fluid mechanics, where we do not have a fixed mass or body of matter, we have a fixed region. So we need certain transformation, which involves, thus we use a Reynolds transport theorem, whose derivation I had shown in the previous lectures, which relates the rate of change of momentum in a control volume to that of a fluid body which occupies the control volume at that time. Note that when you take a control volume or a fixed region, the mass of the fluid which is occupying the control volume changes with respect to time. So this Reynolds transport theorem, for a particular time string, relate the rate of change of momentum in a control volume to that of the fluid body which occupies the control volume at that time. So in the previous lecture, I had presented Reynolds transport theorem, where if you have this capital B as any extensive property, then we have defined an intensive property by basically dividing this B with the mass. This is the mass. So this is small p. So if you apply the momentum conservation, then this capital B is equal to mass into velocity, which is a vector quantity, and the small v is equals to capital B divided by mass. So this becomes the velocity vector. So when you apply to this, when you substitute this capital V and small v, you end up with this equation from the Reynolds transport theorem for momentum conservation. D by dt of m u vector is equals to d by dt of integral of volume integral rho u dv plus you get a surface integral rho u vector u this ur vector dot n ds. Note that here if the control volume is moving, we use a relative velocity. We not only use a relative velocity for, this is basically the normal velocity that we use to calculate the mass flow rate, and this is the velocity, u velocity, which is coming from here. So when we have a moving control volume, then we not only consider the relative velocity for the mass flow rate, but we also consider this as a relative velocity, which I will show you later. So this is from the Reynolds transport theorem, we have obtained the system-wise rate of change with that of rate of change for a control volume. This is the rate of change for a control volume. The system rate of change and the control volume rate of change, they are related with this additional term. Let me explain the physical interpretation of each of this term. Now this term is basically equal to, from the Newton's second law, this is basically equal to the net force that is acting. So we can express this as this is the net force acting on the control volume. This is the rate of change of momentum stored inside the control volume. And this is net momentum flow rate across the surface of the control volume. Across the control surface of the control volume. Note that if you see carefully this statements here, for the rate of, here you have momentum, here you have momentum flow rate. When we say net momentum flow rate in this integral, V means momentum flow rate that is going out of the control volume minus momentum flow rate that is entering inside the control volume. In my previous lecture, I had mentioned that when you in fluid mechanics, there are two rate of change. The first rate of change involves momentum, which is a product of mass into velocity. The second rate of change, which is presented here, involves momentum flow rate, where instead of mass, you have a mass flow rate into the velocity. And for the momentum stored, which is inside the control volume, whereas when you talk of momentum flow rate, this acts on the surface of the control volume. So this is the net momentum flow rate that is going out of the control volume, out of the control surface of the control volume. If you consider a steady flow, then this term, the first term, becomes 0 for a steady flow. So in the next slide, I will present this equation, which is basically correlating the force with the two rate of change on the right hand side. For a steady flow, the first term I'll take it to be 0. So for a steady flow, we'll get F vector is equals to surface integral term, which I've shown here. So in the next slide, for this force equal to this, I will show you that we can do certain simplification and we can express this in an algebraic form. So in this slide, I will represent a simplified form of the equation. So instead of integral form, I will show you an algebraic form of the momentum equation for steady flow. So I have mentioned that for steady flow, the first term in the two rate of change term is equal to 0. So this is because for almost all the problem considered here, you are given the I'll have a separate lecture on tutorial videos. So you will see that in all the problems that we will consider, you are given a single value of velocity at a control surface, but not its variation over the surface. So like if you are given a problem of flow in a pipe, so at the inlet, you are not given the variation of the velocity over the cross section. You are given a single value. So that's why if you are given a single value velocity, for most of the problem you are given a single value velocity at a control surface, but not its variation over the cross section, assuming that the velocity is almost constant over the control surface. Okay, so at all the inlets and outlet, you are given a single value velocity with which you will calculate the mass flow rate. So for almost all the cases, we can use a simplified algebraic form of the momentum equation involving mass flow rate and relative velocity at the various inlets and outlets. Note that here I am presenting a general expression which is also considering if the control volume is moving itself, moving with constant velocity, then you should use the relative velocity to calculate the mass flow rates as well as to take its product to obtain the momentum. So let us consider a multiple inlet and outlet flow system. So here there are two inlets as shown here, 1 and 2, and there are two outlets, 3 and 4. So I am showing you, I have shown two types of M. The curly M I call it as mass, the straight M I call it as the mass flow rate. So this is the product of mass flow rate with velocity. This is mass into velocity is momentum. Mass flow rate into velocity, which is a vector, is a momentum flow rate. This is a momentum flow rate. Entering at 1, this is at 2. Thus, this is the momentum rate leaving at 4, 3, and 4. So and you are given only one velocity at each of this inlet and outlet. Here you are given UR1, here UR2, UR3, and UR4. Okay. So you have a single valued velocity. You are not given the variation of this velocity across the cross section of this inlets and outlets. So for such cases, we can obtain a simplified form of momentum equation, an algebraic form. So the original equation which I had presented in the previous slide was the net force is equals to, for a steady flow, the first rate of change term is 0, rate of change of momentum stored inside the control volume is 0, and you are left with the second term which involves a surface integral where you have rho u vector and u vector dot n, because you take the normal velocity to calculate the mass flow rate, and you have a surface integral. Now here, if the control volume is moving, note that this velocity is also a relative velocity and this is also a relative velocity. Now since for this problem, you are given a single value of the velocity, in general a relative velocity. So what we can do is, if this is not varying, it has a single value over the cross section. Although this surface integral for this problem, you will have 4 surface integral. First delta S1 for 1, delta S2 surface integral for 2, similarly for 3 and 4. So if you take all the 4 surface integral, this UR, the relative velocity at 1, this is not varying over the cross section of this surface. So we can take it out of the integral and we can express this in a simplified form where this F, we can write it like F is equals to product of mass flow rate at outlet multiplied with the velocity vector at the outlet summation over outlet. Now the outlet here are 3 and 4. So basically we are saying M R4 U4 plus M R3 U3. So basically you substitute wherever you have O, 3 and 4 minus summation of MRI. Note that this is URO, this is relative velocity. What I'm using subscript R for both mass flow rate and the velocity, this velocity. The reason is I'm using a general case where let us suppose control volume is moving, then this velocity is the velocity relative to the moving control volume. Control volume is moving with a constant velocity. This is the relative velocity correspond with reference to the moving control volume. Now in the mass flow rate also, there is a velocity which is appearing, which is this. This also is corresponds to the relative velocity. So that's why this mass flow rate is calculated using the relative velocity. That's why I'm using a subscript R for the mass flow rate also. Now, if you mostly, as you might have studied in your earlier course on fluid statics, whenever we apply any vector equation, we apply component by component. So for a 2D case in a Cartesian coordinate system, let us write down the x component and y component. So to write down the x component, basically what we will do, we will write the x component of this u velocity, which is a horizontal velocity, and that I will represent as small u, and the vertical, to obtain the vertical component Fy, we will here have v velocity. So Fx and Fy are given here as so note that we are having for Fx u velocity, and for Fy we are having v velocity. The MR, the mass flow rate, note that they, to calculate this mass flow rate or this mass flow rate, you are not considering the x component or y component. You are considering the normal component. Okay, so the x component appears here only. So this is like a fill in the box type of problem. Wherever I have a circle, if you want x component, then you substitute fx here and the x component of the velocities. You got the y component, you substitute fy here and the v component of the velocities. But outside the box or the circle, the terms that you are having is basically the mass flow rate. And remember that unless and if the control surface is vertical, then mass flow rate will involve the normal velocity will be u, and if the control surface is horizontal, then it will be v. But in general, it is not horizontal and vertical. And in that case, this mass flow rate will involve the normal velocities. So note the difference between the velocities which are involved in mass flow rate and the velocity that you consider for the calculation of x component and y component of the forces. Also note that there are velocities that are involved not only as a second term, but in the first term, that is mass flow rate, the velocity is involved, and both these velocities, if the control volume is moving with a constant velocity, then this velocity is the velocity is a relative velocity where your frame of reference is with reference to the moving control volume. So after presenting the Reynolds transport theorem, first as an integral form and then as a simplified algebraic form, where I have presented that force is equals to net momentum flow rate going out of the control volume minus momentum flow rate entering into the control volume. So, and momentum flow rate is expressed as the product of mass flow rate into u velocity for to calculate Fx, and so to calculate Fx, we are calculating the net x momentum flow rate going out of the control volume. To calculate Fy, I had presented. To calculate Fx, I have presented net x momentum going out of the control volume. For Fy, net y momentum flow rate. Now x momentum flow rate, so let me write it down again. To calculate fx, I have presented this as a function of mass flow rate, where I have taken the relative velocity and the x component of the velocity. And to calculate, to obtain Fy, I have presented as a function of mass flow rate. This is also relative velocity and y component of it. Now the product of mass flow rate with u velocity is x momentum flow rate. So basically, x momentum flow rate is, I have expressed Fx equals to net x momentum flow rate leaving the control volume, where I have, when we say net momentum flow rate leaving, then it will be 3 plus 4, which is outlet, minus 1 and 2, which is inlet. For y, force acting in the y direction on this control volume, these are the forces which are acting on the control volume. For the y component, this is equal to, this involves mass flow rate into v velocity. Mass flow rate into v velocity is the y momentum flow rate. So Fy is expressed as net y momentum flow rate leaving the control volume, where we take y momentum flow rate at 3 and 4 minus 1 and 2. So now I'll have a few slides on how do you choose a control volume wisely. So this is the figure which is shown. If you have a fixed control volume, I'll show you two cases, fixed control volume and a moving control volume. So if you are given a, this is a problem corresponding to, let us suppose there is a tripod. This is a tripod, and this is holding a nozzle. What is a nozzle? No, so this is a pipe of constant cross section. This pipe is connected to a nozzle, where basically you can see that the cross section is reducing along the flow direction. This is your nozzle. So all of you know that when the fluid passes through a nozzle, when it comes out, it has a larger velocity. There is a reduction in the area, and there is increase in the velocity. So in this case, when the jet is coming out with a larger velocity, there is a certain force which acts on the tripod. So to calculate that force, we do basically finite fixed control volume we take. Now the control volume that is suggested for this problem, in the next slide I will show you two types of control volume, and then I'll discuss that why we are taking this control volume. Here we take the control volume which crosses through the tripod, and so there is a reaction force which acts on the tripod. So we will take a reaction force, and basically by applying, so we'll use the expression which was presented in the previous slide. So that is the net external force, which will be reaction force acting on the tripod in x direction, is equals to net x momentum flow rate leaving the control volume. So we will calculate the momentum flow rate as mass flow rate multiplied by the u velocity at the outlet minus x momentum flow rate at the inlet will be mass flow rate into u velocity at the inlet. This will be equal to the net reaction force that will be acting on the tripod. So this is the control volume that we take for a fixed control volume. In a fixed control volume, the velocities that we consider is the absolute velocity, since the control volume is fixed. But if the control volume is moving, like let us suppose this aircraft is moving from right to left with a velocity of, let us say, 300 km per hour, and let's suppose the exhaust gas which is coming from the outlet of this aeroplane, this is at a velocity of let us say 500 km per hour. These velocities are with respect to fixed ground level. So if the net exit velocity with respect to this moving control volume, note that the absolute velocity of the exhaust gas is 500 km per hour. The aeroplane velocity is 300 km per hour. So the relative velocity of the exhaust gas, which is leaving, because to calculate the next net x momentum flow rate leaving, you have to calculate the mass flow rate, as well as you will multiply by the velocity in the x direction. So both these velocities, to calculate the mass flow rate and the velocity u velocity that we'll be considering, both those velocities will be a relative velocity, and the relative velocity will be given by the absolute velocity, which is in the positive x direction, which is in this case it's 500 km per hour, minus the velocity of the control volume. Now the velocity of the control volume is minus of, because it's in the negative x direction, it is minus of 300, so 500, so it will become finally 500 plus 300, which is 800 km per hour will be the relative velocity. So note that using that 800 km per hour as the relative velocity, we will obtain the mass flow rate first, and we will also multiply, because that is the velocity in the x direction, to calculate the x momentum flow rate leaving the surface of the controller. Now this is another problem where I'll discuss that here there are mainly two types of control volume which are presented. This is a control volume which is presented as control volume A, and this is a control volume. So there are two types of dash line. The one which is shown as this pink dash line is control volume A. The black dash line is a control volume B. So if you compare this, the way they have been taken, just to clarify, the control volume A is basically constituting only fluid region. Note that this is not considering, this pink dotted line is not crossing any solid structures. Okay, so if you take this control volume, it is inside this control volume, you have only fluid, no solid. Whereas if you take this black dash line based control volume, it is cutting this nuts and bolts, and you can see that within this control volume B, you not only have fluid, but you have a solid also. Okay. And these are finite size of control volume, and we are doing finite control volume based momentum analysis. So out of the two control volumes, now the question is, once you take a control volume at the control surface, we are supposed to know the surface forces. There are two types of forces. Body force, which is the weight. So if you take a control volume A, then you need to know the weight of water. If you take a control volume B, then you not only need the weight of water, but you also need the weight of this tack and this bolts also, this nuts and bolts which are inside the control volume. Okay, so for control volume A, you only need weight of water, because this is the gravitational force, body force which is acting. For B, along with the weight of water, there will also need weight of the structure which is inside the control volume. This is about the body force. Now, when you consider a surface force, if you compare the surface force which are involved in A and B, in A, note that when the water comes out of the tap, outside the pressure is atmospheric. So you know the pressure outside is here, it is atmospheric. But when you cut here, you don't know this portion of the control volume is control surface is common to both A and B control volume, because here you have a black as well as the pink dash line. So this is given to you in a problem. And but the issue is, if you see the other surface like this black control volume, you know, as far as the surface force is concerned, assuming that the ambient condition is there is no velocity gradient. Now at this black dotted line based control surface, the only surface force that will be acting is the pressure force, and the pressure is atmospheric everywhere. So if you see this black control volume on this surface, this portion of the surface, pressure is atmospheric, that's the only surface force. Here again at the outlet of the tap, the water is coming out with the atmospheric pressure. Here also everywhere pressure is atmospheric. Here, okay, so in the solid you will not bother about the surface forces, and that we will consider the forces as the reaction force. Okay, whereas if you consider this big control volume on this surface, now there will be viscous forces, because there when the water is flowing inside this tap, there is some velocity gradient, and along with the viscosity of the fluid, there are some viscous forces which are acting on this control surface. So if you use this control surface A, you have to apply the viscous forces. Note that these are internal forces. We call these forces internal forces. These viscous forces which act at the inner boundary of the this tab. These are called as internal forces. And whenever we choose a control volume for the finite control volume based analysis, we try to avoid these internal forces. We only want to consider external forces such as this black control volume. You can see the surface is not inside this tab, it is outside, and here the force that is acting is only the ambient pressure creates the force, that is an external force. So when we want to use a controlled volume which is external, not, it doesn't involve internal forces like viscous forces. Other than the viscous, we do not know when the fluid is passing through this tab what is the pressure near to the wall. Okay, so these are unknowns which we want to avoid while choosing the control volume. We want to choose a control volume where we mostly know the surface forces that are acting. So we want to avoid these internal forces. So most of the time we take a control volume which not only involves the fluid but also involves the solid. It basically cuts the solid as shown here. So more wise choosing a control volume is B as compared to A for this problem. Note that in this problem, the objective is the net force on the flange to ensure that the flange bolts are strong. Because note that the velocity in this case, if you consider the viscosity as negligible, the velocity may be almost constant, but there is a change in direction. And this leads to a force in the X and Y direction. So the objective is what is the net force on the flange so that we have, when we design this connection, nut and bolt connection, it is strong enough to withstand that force. So while choosing the control volume, a wise procedure is you lump the unknown pressure and viscous forces together as one reaction forces and represent the net force of the walls on the water. So when we use, let us suppose, a black control volume, we obtain the reaction force, we represent the reaction force from the nuts and bolts. Let us suppose this is Fx and this vertical direction you have Fy. So our objective is to obtain this Fx Fy, where to calculate Fx. What we will do is that we will consider net x momentum flow rate going out of the control volume. At the outlet, you do not have any u velocity. So the x momentum flow rate going out of from the outlet is 0. And from outlet, then you go to minus inlet. In the inlet, x momentum flow rate will be the mass flow rate into the u velocity. So that difference of x momentum flow rate, this will be equal to this Fx. Note that this Fx is a reaction force. If you want to calculate the actual force that is created by the fluid on this bolt, it will be an active force. This is a reactive force. It will be in the opposite direction. To calculate Fy, this is equal to the net y momentum flow rate leaving the control volume. When you talk of y momentum flow rate, you have y momentum flow rate only at the outlet, not at the inlet. Okay, because at the inlet you have u velocity, there is no v velocity. So y momentum flow rate is 0 at the inlet. Okay, so here in this problem, you have x momentum flow rate at the inlet, y momentum flow rate at the outlet. So x momentum flow rate involves the inlet and y momentum flow rate involves the outlet momentum flow rate. So the black control volume is not only limited to fluid as discussed, and this black control volume is more convenient to slice, more convenient to, whenever you choose a control volume, to slide the control surface through solid objects. What is a control volume? Control volume is an arbitrary region in space through which the fluid flows. And what is control surface? It's the bounding surface It is surface that is bounding the control volume. And this control surface can be fixed or moving, that I have shown for the moving aeroplane case. And it is moving with a constant velocity. Note that the Newton's second law that is presented here, or the momentum analysis that is presented here, corresponds to a inertial flow system, where the control volume that you are taking is either fixed or moving at a constant velocity. For flow system which is accelerating, so this the whatever is taught here, you can solve a problem if the aeroplane is moving with a constant velocity and there is an exhaust gas coming out. But if the aeroplane is accelerating, then you have a non-inertial frame of reference. If you take a control volume across over the aeroplane, the control volume will be an accelerating control volume. Then you will have a non-inertial frame of reference. There are equations corresponding to those also, but that is outside the scope of this lecture series. If you see conservation law, the conservation law is very similar to, basically you have to do a bookkeeping. Like in thermodynamics, you keep a bookkeeping of the amount of heat entering, the amount of work, the work generation, the work from the system, and the change in internal energy or enthalpy. So you have basically, and here you are doing bookkeeping of momentum flow rate and the forces. Okay, so this momentum conservation law is basically bookkeeping, accounting of the quantity under consideration. The quantity under consideration are x momentum flow rate going out and in for fx, and y momentum flow rate for fy. Thus, it's extremely important that the control surface is well defined, because if you are not defining the control surface properly, there are more unknowns and you may find that the data for the problem is incomplete. Basically, you should take your control volume such that the data that you are thinking is not given comes out as a reaction force, is a part of the reaction force. You have a velocity at the inlet as well as velocity at the outlet. Both these velocities should be relative to the control surface. This surface force arises, as in the case of that tap problem, when you created the left boundary of the control volume. So basically you were cutting the joint where the tab was connected to the pipe. There is a pressure force which arises in the control volume is isolated from its surrounding. Note that in the tap problem, we have taken a control volume where we have the tap, but the pipe which is connecting the tap is outside the control volume. So when you cut the control volume, which is at the interface of the pipe and the tap, then at the fluid which is entering, it has certain pressure, and the pressure is the surface force that arises as the control volume or the tap is isolated from the surrounding that is corresponding to the pipe. Effect of any detached object is accounted for by a force at that location. Like when you cut the tripod, basically the tripod is creating a fixed support and it's not allowing the nozzle to move ahead. So when you cut it, there is a reaction force that you have to consider that will balance the net rate of change of x moment. This control volume is very similar to in your fluid statics course or dynamics course, you might have drawn free body diagram. So this is similar, this control volume that you are drawing is similar to the free body diagram. You have to choose the control volume such that the forces that are not of interest, like in this case, we are not interested to determine, like the problems that I had presented, flow through a nozzle which was supported in a tripod. We are not interested in or even when you consider the flow through that tap, we are not interested in the viscous force and the pressure force near to the surface. So those are internal forces that I have mentioned. So thus they do complicate the analysis. So we should avoid this internal forces, which was there in that pink control volume, but not in the black control volume. The well-chosen control volume exposes only forces that are determined, such as reaction forces, and it should involve minimum number of other forces. Okay, mostly I'll present in the next slide what are the forces normally the control volume should involve. Other than the reaction forces, there are two forces basically it involves. Only external forces are considered in the analysis. Internal forces such as pressure forces between the fluid and the inner surface of the flow section or the viscous forces are not considered unless they are exposed by passing the control surface through that area. For most of the problem, if you take a control volume, all over the control volume you have certain, so let us suppose the fluid is entering into a nozzle. This is the top surface, this is the bottom surface, and the right surface of the nozzle. This is, here you are having ambient pressure. So what you can do is that, let us suppose you are given this pressure, you can subtract the ambient pressure because it cancels down. So atmospheric acts in all directions and thus can be ignored when performing. So basically you can express the pressure in terms of gauge pressure. So when you do that, all this pressure becomes zero on the surface, and so this absolute pressure gets converted into a gauge pressure. So it's, for a problem, it is suggested that you operate with not absolute pressure but gauge pressure. So as I was saying earlier, that when you choose a control volume, the forces, external forces that you should consider mostly consist of weight of the fluid inside the control volume. When you consider weight, it's not only the fluid that is there, but you also have to consider weight of the structure. But in many problems, if you are not given weights, you can ignore the gravitational force for that problem. And when you, let's suppose there is a fluid is passing through a pipe which is having an 180-degree turn. So this is entering from here and it is leaving. So it's a downward entry and upward exit. So on this U tube, if the fluid is flowing, so you can see that the control volume is chosen such that this is the weight of the liquid as well as this tube, total weight. And when you cut from here, here there is a pressure force which is expressed in terms of gauge pressure as I mentioned earlier. So here the fluid has certain pressure which needs to be accounted for. On the other surface, part of the control surface, note that everywhere pressure is atmospheric. Here on this part atmospheric, everywhere it is atmospheric except at the inlet and exit. Note that this is, I'm assuming that this is not exiting at the ambient. If it is exiting, then this will also be atmospheric. If it is connected to a pipe, then this will be not atmospheric. So these are gauge pressure. So note that here the pressure is involved as a force, the weight is involved as a force, and then you have a reaction force. As I mentioned earlier, other than the reaction force, most of the time we want to generate control volume such that at the control surface we only need to bother about pressure forces, and other than pressure forces we are bothered about the weights. Okay, so we should not take such control volumes where we have viscous forces. Momentum equation is commonly used to calculate the forces, usually on support system or connectors. As I had shown in tripod is a support system, and the elbow that I showed you as a connector, which is basically the pipeline is connected to a water tap through nuts and bolts, so that is a connector. So this momentum analysis that we do mostly is to calculate the forces corresponding to support system or connectors, where mainly the change in the direction of the flow leads to certain forces which needs to be supported. With this, I had come to the end of this lecture 50 on finite control volume based linear momentum analysis. Note that here we have done an integral analysis. We started with Reynolds transport theorem, basically obtained the expression for the net external force acting on a control volume and equated it to the net x momentum flow rate going out of the control volume for a steady flow, where to calculate fx you are interested in x momentum flow rate, net x momentum flow rate going out of the control volume. For that, you subtract the momentum flow rate going out minus x momentum flow rate coming in for fx. For fy, you subtract the y momentum flow rate going out with y momentum flow rate coming in. Thank you for your attention.